So we've made it through the better part of half of this chapter 20. We've gone through that basic introduction to organic molecules and alkanes and the naming system and how we draw them. We're going to move on to the other kinds of hydrocarbons and then add on a little bit more about the other molecules that can be part of this. So focusing on double bonds and triple bonded hydrocarbons, then we can talk about the alkenes and the alkynes. So these would be saturated or unsaturated, just as a bit of a review. These are unsaturated because they're not filled up with other molecules. So those bonding sites are filled up with double or triple bonds. These carbon backbones will be double or triple bonded to themselves. And that's what makes alkenes are double bonds and alkynes are triple bonded. Molecules. So naming alkenes, it's quite similar to the alkanes, except for we're not going to talk about methane. We're going to talk about, I can't talk about methane. We're not going to talk about ethane. We talk about ethene. We wouldn't talk about propane. We talk about propene. And this ene ending is indicating that there are double bonds in this molecule. The location of these double bonds are also numbered for where they are. So we're always going to number our carbon backbone starting closest to that double bond. And so in this one, we would have 1, 2, 3, 4, 5. So it would be propane, but it is not propane. It's pentane, not propane. Pentane, it's pentene because there is that double bond. And we give that number as the 1 because that's the location where that double bond is. If pentene, not pentane, pentene, had that double bond between the second and the third carbon, we would call it 2-pentene. So this ene ending is indicating that's not a side chain, it's a double bond, and that double bond is located at the second carbon. If an alkane also has a side chain or a substitution or a substituent group or an alkyl group, the numbering starts closest to the double bond. So this double bond is taking priority over the side chain. So we want to write the branch names and locations first and then end with the double bond. So this is our first example here. So I find my carbon backbone. So I know that there are 6 in this chain, and so that would make it hexane, but it's not hexane because of this double bond. So it's hexene. The location of this double bond is at the second carbon. So I know it's going to be a 2-hexene. Continuing to work this back, I would label my side chains here. So I've got one side chain. Yep, so we've got a methyl group. And it is at the second carbon. And so working it backwards, we've got the fact that it is an alkene, right? With that double bond where it is, changed the root name to have a different ending. And then we did the side chains, very similar to what we were doing with the alkanes. Alkynes are much the same, except they end in yne. So we continue in finding the longest chain and numbering it in the order that would give the smallest possible number. So this would be pentane, but it's not. It's pentyne. It's pentyne because there's a triple bond here. And I would say that it is 2-pentyne because that triple bond is at the second carbon. Finding this one, taking a look at the longest chain possible and numbering it in the order that gives me the smallest number for my double or triple bond. I can see that there's 5 in a row. It's another pentyne. The location of that triple bond is at the second carbon, and there is a side chain here. So this side chain is at the 4th carbon, and it is a methyl group. So there'd be 4-methyl 2-pentyne as a name. So we'll practice naming these ones, and then we're going to move on to one more variation in our organic chemistry. So always in these ones, we want to find the longest chain. This is in the condensed form. 1, 2, 3, 4. So this would be butene. Ene because it's a double bond, right? These are double, these are triple. And that location would be 2-butene because it's between the second and the third carbon. Again, with these, I think the easiest way is to find the longest chain first. So this would be, again, a butene, 1-butene, and the side chain would be at the third carbon. So 3-methyl, whoops, it's in there already, 1-butene. This one would be a butyne because there's a triple bond, not a double, and I would say it's a 1-butyne. Last one, a little bit more going on, mercifully already numbered, and you can see that we've got one side chain. So we've got this triple bond, so it would be octane, but it wouldn't be octane, it'd be octyne because it's an alkyne, and that is at the third carbon. And then I would label up my side chain here. So 7-methyl 3-octyne would be the name for that. I did say that, you could have different shapes. We talked about isomers and we talked about linear, branched, and also cyclic things. So cyclic hydrocarbons, this was the cyclobutane that was from earlier in the notes. Benzene was one that I talked about, and you can see a little bit more kind of showing up in understanding a double and single bonding pattern in a benzene ring. These are just here for kind of introduction, but a hydrocarbon with the carbon chain joining to itself in a ring structure is a cyclic hydrocarbon. Often glucose is, or fructose, could be linear or it could be in a ring structure, just as an example from biology. So just a bit of an intro to that, really, not very much on that at all. But like as we talk about biology, these functional groups, organic compounds, can have side chains of non-hydrocarbons. And so the key thing about these functional groups is what makes organic molecules soluble in water. So when you have a functional group, this is how we are carbon-based life forms. We're a water-based, carbon-based life form, right? So these types of functional groups are in your data package. You do not need to memorize them. Even just categorizing these can be useful. And so taking a look at your formula pages allows you to see this COCO arrangement here. I always think of that as a Coco, like a Coco Chanel. These esters, and this one down here where there's an O in the middle, this is an ether. These are often for smells and flavors. So I think of Coco Chanel as a perfume. That's an ester group. This oxygen in the middle here would be an ether group. So just again, as introduction, these functional groups are really important because they make these molecules, these hydrocarbons otherwise, soluble in water. This is a common one when you have a hydroxyl group off the end. This makes it an alcohol. And the other one here, where you have this double bonded oxygen off of a carbon, this would be an aldehyde. There are other names. There's ketones, aldehydes. Alcohols are the most common, maybe, that you might have heard about before. So these alcohols, an alcohol is an organic molecule that contains a hydroxyl group. That's the OH bonded on there. Naming alcohols, this is the only one that we're actually going to really give some time to in naming things. Very similar to what we've done before, but we continue to find that longest chain, right? And we want to find that hydroxyl group as the parent compound. And so we want a number closest to that hydroxyl group. So in these ones, we would number these up and name them. So as an example, this would be 2-methyl 2-butanol. And so the alcohol changes the ANE to an OL in these. And you can see a hexanol and a heptanol. There's a few more examples down here. In these ones, we'd want to number them in the order that gives the alcohol the lowest, and this would be butanol. It's weird to not write the whole thing. And these ones, 1, 2, 3, 4, 5. These would be 1-pentanol. Kind of similar concepts, but there's like variations in all of these. So we'd number this one, finding the longest chain, giving the hydroxyl group the lowest number possible, sometimes going around the corner. I would see 7, so this would be heptane or heptanol. It would be on the 3rd carbon, that hydroxyl group, and I do have a side chain here. On the 5th carbon, I'd have 5-methyl 3-heptanol. And that really concludes our discussion of organic chemistry. Such the tip of the iceberg in this, but hopefully that gives you the confidence to take a look at your textbook questions and decode a little bit of the world of organic chemistry.